Hi guys, welcome to, I think we are in week 9. Let me check again. No, week 8, I'm sorry. Okay, welcome to week 8 for Astronomy 120. We are still dealing basically with the solar system. I know we just came off of a big midterm not too long ago, and we still have quite a few things that are needed to be done. So we just came from that exam, and now we're gearing up. We're basically still in the solar system. Just a reminder and refresher what we did so far. Basically, we first explored the Earth. Just before starting the solar system, we saw the Earth as a planet. Then we explored the Moon, and we saw basically, because it's an important object and it's actually something that we visited. I mean, I'm talking we as the human race. And also we had probes on it, we have orbiters on it, and it's still a subject of interest up to this point. So by far, when you look at objects in the outside of the Earth, the Moon is a big deal, okay? So we looked at that. We looked at also, I mean, in trying to decide what else to go for, and usually the decision is kind of, should we do Mars or should we do Venus? So it's not really that hard to make the decision in this case and go for Venus instead, because it bears a lot of similarity with the Earth, but it has also differences with Earth. So it was interesting to explore that, at least from a conceptual point of view, and understand it and see what's going on with it. In studying Venus, actually, if you guys remember, we made some comparisons actually to Mars still. So we made some references to Mars in terms of composition, in terms of atmosphere and things like that. But the focus was actually on Venus nonetheless. So that's basically it as far as the inner planets. We talked hardly anything at all about Mercury, and that's basically it's a planet that is very close from the sun. It has some interesting features also, and actually some research nowadays that claim that basically Mercury was actually a giant planet. It was a gas planet, but it lost its gas immediately. And the reason why this is so is because of the current observations based on the Kepler project that looked at a narrow region in the Cygnus constellation, and was looking actually for exoplanets in there, where we found thousands right now of exoplanets. But they have this peculiar characteristic that a lot of the giant planets seem to orbit their host stars not too far from it, from where actually closer to their host star than what Mercury is, and they are referred to as the so-called hot Jupiters because of their proximity to their stars. So now the speculation, or at least some of the models or theories that are proposing actually that Mercury also was one of those things, but it lost most of its atmosphere. So now what we're looking at is basically its core, okay? So that's something that we did not explore and we didn't study. Again, it has some relevance in terms of astronomy because of its, basically it's always moving very close from the sun and things like that. So this is where we are so far in terms of the content. We also are going to move on to the outer planets. And again, we're not going to go for all of the 4 outer planets. We're going to focus on the 2 biggest ones, namely Jupiter and Saturn. Granted that if we don't really talk a little bit about Uranus and Neptune, they're actually slightly different in terms of their composition. Uranus and Neptune are the so-called ice giants because of their distance from the sun, versus the other two, which are actually gas giants. But they have similar properties in a sense. First of all, they are big, they have a lot of moons, and they have similar composition, more or less, in terms of chemical composition, basically hydrogen and helium as the main components for all of these objects. The other two, they have bluish colors because of the methane, the gas that you use to in your oven, basically the one in the kitchen. So that's because that's basically some of the differences between these two. So the focus is going to be again on just Jupiter and Saturn, and then we're going to study their moons. We're going to study satellites in general. So it's not necessarily the moons of the outer planets. We already saw that the inner planets really do not have moons. Earth is an exception, okay? Earth is an exception. So when we say satellites, we're going to be talking mainly about the outer planets' moons, okay? Namely the moons of Jupiter the moons of Saturn, the moons of Uranus, and the moons of Neptune, okay? So that's what we're going to be talking about. One moon of Neptune, we're going to defer its discussion. And this is the biggest moon, actually, of Neptune, namely Triton. We're going to defer that discussion for the unit that comes after, basically the icy world. Because you will see when we talk about Triton that it is not really a moon. It's a captured dwarf planet that became a moon of Neptune. And there are a lot of reasons for why that is, and we're going to explore that down the road. So again, after we finish with the outer planets and their moons, we're going to move to the icy world, namely the dwarf planets and all of the other objects that are past Neptune, the so-called trans-Neptunian objects. We're also going to talk about the comets, and that concludes the solar system. So we really, after these 2 units, we still have 2 more units after that. So we still have 4 more units to cover all of the things that potentially we could cover about the solar system. And then we're going to go back to the units in the 20s, 21, 22, and so on and so forth, where we're going to be talking about the prelude to the study of the stars. We're going to study light, okay? I know some of you are sitting in my astronomy class, and you know that we did in a lab already on spectroscopy, and we still have another lab down the road using spectroscopy actually to study the Pleiades and some of the objects in there, to see basically the light that comes from them, collect the light and do all kinds of stuff from them. So for those sitting in that class, so basically they know exactly a little bit more about these things, but it is interesting before we go into the stars actually to learn about that branch of science, which comes from physics, which is optics, spectroscopy, which is kind of electromagnetism and things like that. So we're going to go a little bit more into that. We're going to discuss the wavelengths, the frequency, the dispersion law, and mainly the characteristics of the different elements in producing those lights. We're going to discuss something called the beam displacement law, okay? And also that gives us the temperature as a function of the maximum wavelength, which is a critical piece of information, because as you look at a star, just by looking at its color, you could determine its temperature, which is like magic, really. It's amazing. All you have to do is just find the peak frequency, meaning what is the maximum frequency where that star is emitting at. Based on that, use a simple formula, and you can find the surface temperature of that star. Then we're going to use some other laws, basically, that tells us how light basically propagates in space, to be able to determine the distance of stars. Because if you know how much luminosity that star emits, how much light it produces, basically, and compare that to how much it is bright. So basically, you take a candle, and you know how much light that candle produces. If it's close from you, it's going to shine big. I mean, you're going to have a lot of light from you. If you put the candle far away from you, then it's going to light less and less depending on the distance. That's exactly what we're going to be doing, trying to find the distances to this star. So this is one of the methods. And again, there is another law that we're going to use. It's not just the displacement law due to Mr. Bean. Also, we're going to use the Stefan Boltzmann Law, which is actually something that actually comes also from physics, that tells us that if I know the temperature of a star, remember, okay, so I know I'm a little bit ahead of the discussion, but I like always to bring the topic up front before, so give you at least an idea, so that when we're doing it, it doesn't come as completely new surprise to you guys and you're completely shocked into finding a lot of stuff coming at you. So I'm just putting stuff in here. We're going to discuss this more in detail, and hopefully you're going to see it. So in addition to the displacement law that the people sitting in 125, Astronomy 125 have seen, we're going to have something called the Stefan Boltzmann Law, which is going to help us to, so if I know the temperature, remember, if I know the color, I know the temperature. Then if I know the temperature, I know how much light that star produces. And if I know how much light that produces, compare that to how bright the star is, then I know how far it is. It's amazing, really. I mean, when you put things together, I mean, we're here sitting in a very, very, very small rock, looking at faraway objects and studying them, analyzing them, and telling what they have and what they don't have, how old they are, how far they are, and what's going to happen to them in the future, and things like that. So it's really fascinating topic. So yes, we're going to conclude. We're not going to spend a lot of time actually on the solar system because we still have other things. We need to learn about the stars. We need to learn about basically globular clusters, basically when you have a lot of stars sitting together. And that's actually one of the labs, as I was saying earlier, about the Pleiades. There is the Hyades also, which is another globular cluster not too far from it. So there are all kinds of interesting objects out there that we can explore. And then that's not it. You still have a lot of stars, billions of stars coming together in galaxies, and then galaxies interacting together in local clusters and local groups, I should say, and clusters and so on and so forth. So again, we still have a lot of things to cover. So we are probably right in the middle right now, and we are actually right in the middle of the semester. So we are exactly where we're supposed to be. So this is basically where we are. Okay. So let me share with you the stuff from this week. Share. I know you guys have been looking at this probably because it was published, I think, yesterday or the day before or something. So yeah, we have this assignment, so please take care of them. This is from the previous week. This is from this week. This one is due this Saturday. The other one is due the Saturday after. You have a homework assignment that's still kind of a little bit far in the future, but we're going to discuss it either this Thursday or next Thursday, depending on basically the time allotted for it. And we will have other assignments coming down the road. So this is not the end of all of the assignments in terms of homework type. The other thing, and that's why I brought this page in here, is the lunar observation. Please do not forget about it. Yes, it's still due on October 6th. No, the lunar observation is October 6th. Today is October 4th. So the third observation is actually this Thursday, okay? Which means that tomorrow you're going to go and spot basically where the moon is and things like that, and do the stuff in the evening or early in the morning until you find and you're satisfied and you document your observation, and then you go to the next day and you actually do the actual observation. I don't see any problem with the weather in terms of clouds, so everything should be fine. And you could, if you can find it early in the evening, maybe check a little later in the evening or early in the morning or in the morning, so it should be fine. You should be able to find it. If these two cannot work, namely tomorrow and Thursday, then you still have your Friday observations, and that concludes everything. Okay, so this is just I want to bring it to your attention so that you guys are on board with this thing and you're on top of your assignments. This week, usually after the exams, they tend to be a little bit light in terms. I mean, I'm not saying light, relatively speaking. Yeah, you have 3-4 assignments that are still due, so it's not really light, but compared to the usual stuff where the things start to build up little by little, leading to the midterm where things start to basically heat up. And then after that, we relax a little. And that's basically human nature. So we can't really work at full speed all the way through and through. That's going to be too much. It's going to burn people and it's not really advantageous. Okay, sounds good? Okay, thank you, Kiara. Okay. Thank you. Yeah, Samantha. Okay, so let me share with you my notes. We are in unit 45. Okay. So again, the focus today is going to be on the gas giants, namely Jupiter and Saturn. Okay. Jupiter, of course, these are the objectives. We're going to describe the main features. So if you have even a 5-inch telescope, which is a small telescope, you should be able to see Jupiter with its main features. If you happen to have a filter for the planet Jupiter, then you should be able to see the colors, which is really amazing, okay? So, but you're gonna see those lines basically that form on it. So that's the main features of the planet. So that is really, and then the other feature in it is this red spot that we're going to also examine a little bit more about it. And then we're going to talk about the interior of the planet and describe its internal structure. So before I do that, let me stop sharing the screen and share with you a beautiful picture, fresh from James Webb, okay, about the planet Jupiter. I think it came about 2 weeks ago or so, okay? So this is the picture from the James Webb about the planet. One of the things that with your own telescope, or even with more powerful telescopes, you're not going to be able to see, and that is the rings of Jupiter. Jupiter has rings too. As a matter of fact, all the outer planets have rings. Saturn has rings that you can see even with even with binoculars. As a matter of fact, you should be able to see the rings of Saturn. So Saturn has rings, and this is one of the things that Mr. Galileo puzzled him. Didn't understand what's going on with it, and so he thought that they're kind of ears to the planet, and then that's how he drew them actually around the planet like that. And then in his sketches basically of the planet, because he was using the telescope to look at Saturn. And then also, but he didn't see that. He saw the moons of Jupiter. This picture is very, very close from Jupiter using James Webb. And James Webb, if you guys don't remember already, James Webb is works in the infrared. Basically, if you were to look at this image the way that James Webb produces, you cannot just look at the black picture, because we don't see the infrared. We did not evolve to see the infrared. So it's like goggles basically that are used for hunting or for military applications or for night vision. Those goggles basically, if you look at, for example, a deer, and that at night, the deer will give you the shape of the deer, okay? Because they take the infrared and they convert it for your eyes to see, okay? But if you remove the goggles and look at the what the goggles are looking at, you don't see anything. I mean, it's all dark in there. You don't see anything. So that is the same feature in here with the James Webb. It works mainly in the infrared, something that the Hubble telescope cannot do. The Hubble telescope operates mainly in the visible range. So basically, the Hubble telescope will see what we see, but this one sees stuff that we don't see. And that's why it was able to find these rings. It saw the rings of Jupiter. We knew they exist. I mean, we were able to find them using when we had the missions that went in there. So we were able to find the rings, and they have a similar structure, albeit they're a lot less dense than that of Saturn. That's why we couldn't see them in the visible light. So that's one of the features that this one has. As a matter of fact, what's the name for Uranus? We found them, we saw them when Uranus was passing in front of a star, and the star was dimming in and out. That's where we discovered also that actually Uranus had the rings. And then for the same thing for Neptune, and then now we know that all of the outer planets have rings. So this is one of the features one of the pictures that James Webb had produced. The other thing interesting about this picture is the northern and the southern auroras. Unlike those of the Earth, the auroras on Jupiter, they're permanent features. They stay there and they basically move around. So they're there. So unlike the Earth, which has auroras, but they're basically depending on the activity of the sun, we will have them. These are permanent, and that is because of Io, actually. Io, which is the closest moon to Jupiter from the big moons. Okay, we have other moons closer to Jupiter, like for example Amalthea, but you have the big moon of Io is under tremendous stress. We're going to talk about this one due to gravity from Jupiter. It's pulling on it very tight. But then you have 3 other moons, big, nearby, that are pulling it also. So there is a tug of war. At some point, Io will be on one side, and Jupiter, Europa, Ganymede, and Callisto will be on the other. So they're pulling on it on one side. And then on the other side, some other time, because it's moving super fast, Europa, Ganymede, and Callisto will line up against Jupiter, and Jupiter is still pulling on it. Jupiter is by far the biggest player in this thing. So it's kind of, so it's losing stuff. So it's the most active volcanic, basically, object in the solar system is Io. So it's losing materials, and they spiral in and they fall because they charge particles and produce these beautiful auroras that James was able to see. I mean, with a normal telescope, you're not going to see the auroras. You have to have the missions that went in there to basically be able to see it. But now we see it, and because Jupiter has a magnetic field that is far greater than that of the Earth. So that's why the particles leaving Io, when they go in, they spiral and produce these images that are permanent images. There was another article that came in about I think a week or 2 weeks ago, I saw just the abstract of the article. Honestly, I didn't read the whole thing, but basically what it says is, we know from when we learned about Venus, Venus is the hottest planet in the solar system, but there are cycles on the surface of Jupiter. We will see that the temperature of Jupiter is about 130 Kelvin. 130 Kelvin is nothing. I mean, right now we are sitting at about 300 Kelvin. Just to give you an idea, 300 Kelvin is what you and I right now are experiencing. So when somebody tells you it's 130 Kelvin, this is like negative 150 degrees or something. So it's super cold. So it's gonna, the water freezes in here at those temperatures, no problem. But at some point, the surface temperature of the clouds increased drastically to a point that it's hotter than Venus itself. So that was a puzzling issue for a long time. Scientists didn't understand what's going on. But because of the pictures that came from James Webb, now this article claims that those temperatures are actually the cooling from these auroras from the northern hemisphere and the southern hemisphere of the planet. And they propagate in all directions, basically, basically because of the contact of the different layers. And they go in and the entire planet heat up, basically the upper surface, and they cool. So it seems like this James Webb is bringing us a lot of information about the planet that we didn't have access to, at least according to this article. But now the whole thing I really brought this picture in here is because of the rings that we couldn't see in the past and the beautiful image that James Webb was able to produce for us. So let's continue with the unit itself. So again, these are the objectives. So some basic facts about the planet. Jupiter is about 5 astronomical units from the sun. So basically from the Earth, it can be as far as 4 astronomical units if the Earth and the Jupiter are on one side of the sun. So if the sun is one side, so this is from here to here is 5 astronomical, the Earth is 1 astronomical unit. So it's about 4 astronomical units, okay? About, not exact, 4.2 to be more specific. And some other times the Earth will be on the opposite side of the sun. So the sun will be in the middle. So add 1 plus 5, so it's going to be about 6 astronomical units from us. This fall, right now, it's actually about 4 astronomical units from us. It's going to be as close as possible from us. This was a homework assignment from a few weeks back when we had it, where we're supposed to find the angular size of Jupiter depending on how far it is. When it's at the closest from us and when it's the furthest from us. When it's closest from us, it should have the biggest angular size, meaning if you look at it at sky, it's as big as it's going to get. The variations inside are so slight. Why? Because it's far away, okay? Had it been closer to us, then we will see it growing and shrinking depending on how far it is, okay? Obviously, this cycle it takes a long time because the planet, according to Kepler, takes about 12 years to go once around the sun, whereas the Earth goes once every year. That's basically how the definition of the year is, at least on Earth. In terms of size, Jupiter is about 11 times bigger than the sun. So the sun radius, or diameter, the radius is about 6,400 kilometers. Jupiter radius is about 70,000 kilometers. So if you take 6,400 and multiply it by 10, that's 64,000 kilometers. So you're still short about another Earth, okay, to make up Jupiter. So that's basically the size in terms of the size. So that's one thing. In terms of mass, Jupiter is about 300 times the mass of the Earth. Okay, there is kind of an improportionality in here, and I will explore that thing in here. So the first question I want to ask you in here, and it may be a little bit confusing, but I'm hoping that it's going to be clear soon, is this. The mass is 300 times bigger. The diameter is only 11 times bigger. So what happened to the size, the physical size, the volume itself? The volume actually is more than 1,000 times bigger. So in other words, you're going to take the Earth, and you need the thousands of them to fit inside Jupiter. Why? Because the volume is proportional to the cube of the diameter, or the cube of the radius. Remember, the diameter is just twice the radius. So if you say cube of one, it's cube of the other. That means that 11 times 11 times 11, which is clearly more than 1,000, because 10 times 10 times 10 is 1,000. So in terms, yes, the mass is only 300 times, but the volume, the physical size, this is about 1,000 times bigger. So this is one point in here of interesting. For Saturn, it's about twice as far away from the sun as Jupiter is. So Jupiter is about 5 astronomical units. This is almost twice as far away. Just to give you a sense of the size in here, okay, of things. From the sun, you travel, you first find Jupiter, Mercury. Mercury is very close from the sun, about 0.4 from the sun. Then about 0.7, 70% of the way to the Earth, you find Venus, then Earth, then about a time and a half, the distance basically from the Earth to the sun. So the Earth to the sun is one distance, and half of that, that's when you find Mars. So at this point, basically, you travel about time and a half, you found 4 planets. You have to travel a long time after time and a half to find just another planet, namely Jupiter. So you have to travel 4 more times the distance you travel to the Earth in order to find Jupiter. This is its closest approach, of course. It's closest distance from the Earth. So if you're traveling by feet, and it took you for, let's say, for example, you travel 10 meters to the Earth, then you really have to travel 50 meters to find where Jupiter is. So 4 times. That is if it's on this side. If it's on the opposite side, of course, you are going to travel 60 meters. Okay, the 10 meters to the Earth plus the 10 meters from the Earth to the Sun, then the 50 meters to from the Earth, from the Sun to Jupiter. So this is something to give you a sense of size. And now, if you really want to get to Saturn, which is the planet after Jupiter, all that you have covered so far, up to Jupiter, you have to cover it again just to get to the next planet, which is Saturn, just to give you the sense of scale of things. Just to give you an idea, you have to travel again, how far you travel from the Earth to Saturn, just to get to the next planet, Uranus, which is about 20 astronomical units from the sun. So just to give you an idea of how big the solar system is, you go nothing, you're in Mercury. You go a little bit more, you are in Venus. You go slightly more, now you are on Earth. Just take a little bit of, when they're a little in, you're now in Mars. To start covering the rest of the planets, these outer planets, you really need a lot of things. Just to give you an idea now, from Uranus to Neptune, you have to travel as much as you traveled already from Saturn to Uranus. Just another 10 astronomical units, about 30 astronomical units altogether, from the sun to Uranus, just to give you a sense of distances. I mean, they're ridiculous, okay? So huge distances. And then also in terms of the size, this planet is only about slightly less than 10 times the size of the Earth. Again, slightly less than 1,000 times in terms of size. So you're going to have about 1,000 Earths to fit this planet. Obviously, here you need more than 1,000 Earths, as a matter of fact, because 11 times 11 times 11 is more than 1,000. 9.5 times 9.5 times 9.5, slightly less than 1,000. So basically, you make a comparison between the two. In terms of mass, the Earth's mass is about 100 times. So although in terms of size, they're approximately the same, namely Jupiter is slightly bigger than Saturn, but in terms of mass, Jupiter is a lot more massive than Saturn. Yes. So let me stop sharing that screen in here and let me share with you another thing, because it's interesting to see what this means in terms of composition, because it's very, very important to really relate this sizes and things like that. So let me share. Let me find the OneNote. Okay, so here is what we said. No, I don't want this pen. I want a different color. Draw. Let me use the black color. So again, so Jupiter, I want a darker, thicker one. This one is good. So Jupiter, in terms of radius or diameter, they have the same thing, okay? It's about 11 times that of the Earth. Remember, the Earth diameter is about 6,000, Earth radius is about 6,400 kilometers. Meaning, if this is the Earth, and this is the center of the Earth, from here to here, it's about 6,400 kilometers. That's what that rate is. Twice that, about 12,800 is about is its diameter. Okay, the radius of Jupiter is about, I mean, the diameter, the radius of Jupiter is about 70,000 kilometers. It's the same distance, except that this is basically about 11 times as big. In terms of mass, Jupiter is about 300 times Earth's mass. Okay, I know the Earth mass is about 10 to the power 24 kilogram. Take that number and multiply it by 300. That's how much mass the Jupiter does. So in terms of density, if you guys remember, when we talked about the Earth, the density of the Earth is about 5.5 kilogram per liter, meaning you take it on average. Okay, yes, if you go to the mantle, the Earth mantle is about 3 kilogram per liter, but inside the core, it's far more denser than the, but on average, the stuff from the Earth weighs about 5.5 kilogram for every liter. Liter is basically a bottle of water, okay? The big one, not the small one. The small one is half a liter. Actually, we'll say 500 milliliter or 1 liter. If it's 500 milliliter, that's half of that. So you have to fill it twice as much as Earth, and it's going to weigh 5.5 kilograms. So that's what the density really means. So my question now is, what is the density of Jupiter? In other words, is Jupiter made up of the same stuff as the Earth is? So how do I find the density of Jupiter, where the density, its mass over volume? That's all. Well, the mass of Jupiter, I said it's 300 times the Earth's mass. So the mass of Jupiter is 300 times Earth's mass. We just said that. And the volume of Jupiter, remember, the volume is I mean, I'm going to give you the formula, but it doesn't matter really if you don't know it. 4 pi over 3, the radius cubed. So what that matters is this cube radius, okay? So if I take 11 times 11 times 11, I'm cubing the radius of Jupiter, but in terms of the radius of the Earth. So the volume of this planet is going to be 11 times 11 times 11 times the Earth volume. Earth is volume. So whatever the Earth is volume, you're going to multiply it by 11 by 11 by 11. So 11 by 11 by 11 is, I don't care about the numbers in here. I'm going to show you exactly what that means. Let me share a calculator because I really don't feel like we should really do the numbers by hand. Let me share. Do we have a calculator up and running? Let me get a calculator first. Here it is. And let me change it to, yeah, keep it, that's fine. So let me share. It really, numbers, they tell another story, and that's why it's very, very interesting really to explore them, because numbers, they give you a perspective that you really need to see, because we're going to compare that density to the Earth density, and we're going to come up with a conclusion. Is Jupiter similar in the composition than the Earth or not? So that's basically the question that we're going to answer. So again, 300 divided by, and I'm going to write it exactly how I wrote it. I'm not going to do the powers and all of that stuff, okay? Divided by, except I need parentheses. Where are the parentheses in here? No problem. Divided by 11. So whatever the answer is, I'm going to divide it again by 11. So that's the same thing of what I'm doing in there. And then whatever the answer is, I'm going to divide it by 11. So I divided by 11 times 11 times 11. So I divided by 11 and then divided by 11 and divided by 11 3 times. So this is the number. 0.225. So I'm going to write 0.225 in my notes. Share. So this ratio here is 0.225. I'm going to multiply it by the Earth's mass divided by the Earth's volume, but that's the density of the Earth itself, which is 5.5 kilogram per liter. So this one is going to be 5.5 kilogram per liter, because that's exactly what the ratio of the Earth's mass to its volume. That is its Earth's density, which we said on average is 5.5 kilogram per liter. So what I'm going to do now is multiply that answer by 5.5, and I know now the density of Jupiter. So I'm going to stop sharing, and I'm going to share again the calculator with you guys. So whatever this number is, which is 0.2253944, whatever. So I'm going to multiply it by the density of the Earth, which is 5.5. That's it. And magically, the density of Jupiter is not the same as that of the Earth. It's 1.239 according to this calculation. The numbers I gave you, 311, are approximate numbers. As a matter of fact, the volume of the diameter of Jupiter is not exactly 11, it's slightly less than 11. So if I put the correct numbers, I will find a better answer than this one. And it's very close to 1.3 rather than 1.2. Right now, it looks like the answer is 1.2, but as a matter of fact, it's 1.3. Okay, so it's not too far. I mean, we're off by just a fraction and basically 1 point out of 10. Okay, so it's not really that 1 point out of 100 in this case. Okay, so it's not even that big of a deal. But the point we can here is the density of the planet. So let me share with you this in here, which we just basically did with this simple numbers that we have. The density of Jupiter then is about 1.3 kilogram per liter. So from here, we know that Jupiter cannot be made up of the same stuff as the Earth does. It has to be made up of lighter stuff. Okay, it has a lot of it, but it's lighter stuff. That's why it's a gas giant. The density of water density, so that you guys know, is equal to 1 kilogram per liter. This is slightly more than that of the water, that's all. So if you take 2 bottles of 500 milliliters of water, or 1 full bottle of 1 liter of water, and you weigh it, it's going to weigh 1 kilogram. Jupiter weighs slightly more than that. That's all. Okay. So Jupiter, because it has an inner core that is dense and has a lot of stuff, so basically that's what happened to it. If you do the same analysis with the planet Saturn, remember Saturn, we're going to have 100 times divided by 9.5 times 9.5 times 9.5. That is because each radius of the Saturn is about 9.5 times bigger than that of the Earth, times, of course, the density of the Earth. You're going to find the number very close from the correct number, which is about 0.63 or 0.65. The correct number is very close from 0.7 kilogram per liter. Compare that to what? Quickly. This is less than water. So Saturn is less dense. So this is Saturn, by the way. Saturn is less dense than water. So if somehow you could have big enough ocean, there is not enough ocean on Earth, by the way. You have to have an ocean, a huge ocean, okay? The size of which you have never heard of. I mean, it's unbelievable. But if you do somehow, Saturn actually will float because it's less dense than water. Its density is 0.7 kilogram per liter versus that of water, which is 1 kilogram per liter, and the density of Jupiter is 1.3 kilogram per liter. Just to give you an idea of the sense of things and how they are. That too suggests that it's also made up mainly of a gas too, and it's a giant because it's about 10 times bigger than the Earth. So that's basic 10 times in diameter only. It's about 1,000 times bigger than the Earth. Okay, so it's big. In terms of comparison of sizes, obviously this is where Jupiter is. This is how Saturn is. So Saturn is slightly less than Jupiter in terms of size, but this one has far more stuff piled up. So it's the outer one, namely Jupiter, had far more stuff, but it not really 300 times versus 100 times. So it has 3 times more stuff than Saturn is, yet it occupies slightly bigger volume. So it's more compact, more denser. And that's exactly what these numbers are saying. So the more you pile up stuff, the more you put gas, apparently. It's like the pillow analogy that we gave for the Earth. The more stuff you're going to put in here, they don't necessarily add more upward because they will press more and more, and the volume does not increase proportionally. So in other words, if you take a pillow in here, this is how much space is. If you put another pillow on it, it's hardly going to make the other one slightly less. If you make a third pillow in here, they're going to start pushing down and pushing down. At some point, you're going to be putting more and more pillows, and the more they put, they pressure more, and then it's really not going to increase the size any further. That's exactly what's going on with these objects. One of the interesting things, since we mentioned already the Kepler project for the outer planets, the exoplanets, some of this, oh, no, I'm sorry, I'm confusing something with something else. It's not the outer planets, it's actually the red dwarfs, which are actually stars. Those stars, albeit they're far, far more massive than Jupiter, they're hardly any bigger than Jupiter. So in other words, Jupiter is actually almost a size limit for how a non-star can be. In other words, if you put more stuff, their only thing is they're going to press more and more. The density will increase more, and that's the end of it. So until at some point, if you put some more stuff, that, I mean, it's going to change from being a planet to being a brown dwarf, which is a kind of a star that doesn't have nuclear fusion in its core. But then if you continue piling up stuff, that's what's going to happen to it. It's going to fuse hydrogen and becomes a star. And that's actually some of the literature you might encounter when reading about Jupiter, is that they refer to it sometimes as a failed star. So it did not grow enough to become a star. A brown dwarf is. So this is what I was talking about in here. So brown dwarf are for sure failed stars. They are now actually referred to as stars. Their first surface temperature is far greater than that of Jupiter, but they are not really doing nuclear fusion, at least the one that we know for the main sequence stars like the sun and things like that. So that should give you an idea about this size stuff and what's going on with them and the densities. So that is the telltale sign of those numbers and what they tell you exactly. So when you look at a planet and you find its mass and you find its size, then as an immediate consequence is what's made up of. Look at its density. So that's one of the things that scientists look for. Once they find a planet, of course, depending on how fast it orbits the star and if there it has a moon or something, that is actually, it's very easy then to use Newton's laws and find its mass. Okay, the third law of Kepler combined with Newton's laws and you find its mass. Okay, and for those sitting in Astronomy 125, that's exactly what they're going to be doing to find the mass of Jupiter, as a matter of fact, using Io and tracing Io down until we find the mass of Jupiter, and that's a lab that is not too far from now. Okay, so once you find an object orbiting an object, then you can find its mass. Now, if you can somehow find the size of that object, now you have the volume, then you know its density. Once you know its density, that tells you a lot about its composition. What is it made up of? Depending on its surface temperature too. Okay, so you can tell a lot about an object just by these two numbers. So I know I took a little bit more on this topic in here, but I'm hoping that you guys really appreciate these things, okay, and what they mean. So in terms of the surface layers, we have this dark layers in here, dark lines in here in this structure, which are called belts. And then you have the light zones, which are actually in between those dark belts. So that's the main feature of the Jupiter, at least. For Jupiter, it has this hurricane, or what is it, that the spiraling basically features of the planet. The wind on this planet, all of them, all of the outer planets are moving super fast, okay? Remember, Jupiter does about 10 hours to go once around it's 9.9 hours, basically 10 hours, okay, to go once around its axis. So it's moving super fast. Its upper temperature is about 160 Kelvin. 160 Kelvin, as I was saying in the beginning, is nothing, okay? Its composition is mainly hydrogen and then helium, which is what the sun is made up of, basically. But with traces of other elements, okay, like methane, ammonia, and water. And actually, those methane, ammonia, and water are the ones that gives it this, excuse me, this kind of coloring on the surface of it, okay? There's different shades of the colors on the surface, okay? Because it's spinning so fast, it's kind of, because it's big and spinning fast. That's the thing with it. So it's kind of bulging a little bit. It's flattened a little bit, okay? So those are some of the features of the outer planets, and that's not too far from actually how Saturn would look like too. Saturn temperature is the one that is 130 Kelvin. So I mentioned earlier in the beginning that's 130 Kelvin actually, because remember Saturn is further away from Sun, so typically yes, it has to be cooler than Jupiter is. Okay. Saturn has more tilt than Jupiter. Jupiter is almost on the ecliptic. I mean, perpendicular to the ecliptic. But Saturn actually exhibits seasons just like the Earth does, because its atmosphere actually a little bit more exaggerated because its tilt is slightly bigger than that of the Earth. It rotates super fast also. Because of that density, the composition is about 96% hydrogen. That's what we know of. About 4% helium and traces of other elements, basically. Also, it has these similar features. It has those parallel bands similar to Jupiter, but not as distinct as that of Jupiter. Jupiter, clearly, you can see these features. If you have a telescope, honestly, and you look at Saturn, you will just see white, basically, object, okay? So it's not, even with the powerful filters, you hardly are going to distinguish these lines, okay? But up close, it has also similar structures. It's also flattened for the same reason as Jupiter is, big, spinning super fast. Spins slower, slightly slower than Jupiter, but that's the feature that it has in here, okay? We don't know, honestly, if these planets have a core like the Earth does, because no one was able to go there. But these are the models that we have, at least for them. And these are usually numerical models that gives us basically an insight of how these planets work, and we rely on them. Because of the force of gravity, as the example I was mentioning earlier about the pillows, when you pile them up and what happened to them and so on and so forth, the gas underneath is more compressed than the gas in the upper atmosphere. And because of the higher compression, the temperature is higher. So it's higher pressure, higher temperature. There is an ideal gas law that we're going to discover later on when we talk about the stars. And the ideal gas law, this is from chemistry, if you ever take chemistry, but we're going to talk about this one also. Basically, if you take a gas and you compress it, the temperature and the pressure increases, the temperature increases if you somehow maintain the volume constant. Or if you maintain the temperature constant, the volume shrinks. So this is what the law says, okay? So that you guys understand it. N is just a constant number in here. It tells you how many elements of gas in here, how many atoms in here you have. It's called the number of moles, okay? So if you took chemistry, you know exactly what this thing is. If you didn't, it's a number, okay? It's usually 1, 2, 3, 0.5, 0.2. That's what we do in chemistry. But for this case in here, it's going to be the number of the volume that you're trying to study, okay? So the number of moles. Okay, there is no S, there is no E in it. R is just a constant. R is just like a number. Okay, R is just a constant in this case, 8.314. What is it? Joules per Kelvin. It's just a constant, okay, by moles, the number of moles by mole. So it's just a number. It's always this number. It never changed. That's basically what the experiment has shown. So these two numbers, ignore them. The main thing in here is temperature. Okay, so as you go down and down, the pressure increases up and up, and with it, the temperature go on up and up. So that's basically in a nutshell what this thing is. Okay, if you have the dusters that you have in your home that you go and buy from the grocery store to basically clean your keyboard and things like that, when you release the pressure, the air is compressed inside. So when it comes out, so the pressure basically is being released, you notice that your hand is getting colder. So in other words, when the pressure now goes down, the temperature is going down. That's basically what it is. You notice that your hand is, after a while, you get it too much. So that's basically what this law is. So that's exactly what's going on in these planets in here too. So the temperature inside these planets is super high, but not high enough to start nuclear reactions, okay? But it's high enough that there is a weird state of matter that we don't really understand, that the hydrogen, remember hydrogen is 1 proton and 1 electron. That's what the atom of the hydrogen is, okay? You have one proton and one electron in the atom. Okay, so that's it. This number is one proton and one nucleon. So basically, there's another kind of hydrogen that has a proton neutron, but that's a rare hydrogen. This is the main hydrogen that you will encounter. So basically, when you compress this gas to this state that we cannot even do in the lab in here because it's really ridiculously extreme case, that the hydrogen starts to become more a liquid. So the hydrogen becomes a liquid hydrogen. Not only that, but this hydrogen, because it has one electron available to float in that liquid, that hydrogen becomes a metal. So it's a metallic liquid hydrogen in its core. So here is what's going on then. You have a metal similar to the Earth nickel and the iron in its core, and it's hot, and the planet is spinning super fast. That leads to a magnetic field because you have a current. So when you have charges moving super fast, spinning inside the core, that creates a magnetic field. That's what you have. That's why you have a magnetic field in this planet. Okay. Period. End of the story. And their magnetic fields are ridiculously high. Okay. So again, in the upper atmosphere, you have what is known as you have gases, mainly hydrogen with a little bit of helium and traces of other stuff. But as you go down and down, you have a liquid hydrogen, and inside we theorize, we speculate that maybe there is a core, because that's how all planets grow according to our models. They grow from planetesimals, which are made up of the same stuff that the planets grow from, but because the initial formation will kind of force those heavier, more denser materials to go inside the core, just like what happened with the Earth and what we believe happened with the other planets also. So now you have the same stuff that formed the Earth and all of the other planets most likely also exists also in these planets, and they have actually a solid core. That's what we think. Again, at this point, there is no way, we don't have enough technology to even penetrate just to get to these levels. But these are the models, basically, of what we have. But this explains beautifully the magnetic field of these planets. So this is basically what this whole discussion is. So again, the density and all of this stuff in here, whereas the density of Jupiter, Saturn is about 0.7 kilogram. So again, this is actually the winds. They are driven by that high temperature. Remember, the inside is higher than the outside, and because of the circulation of the air, so it's going to generate winds. And those winds, they form those bands, basically, that I was talking about earlier, the dark bands and the light bands. So regions where the air is falling and regions where the air is rising, okay? And those basically, they create those circulation of the air in their atmosphere. Remember, the inside is super hot. The upper layers are cold. 160 Kelvin is super cold for the case of Jupiter. 130 Kelvin is even cooler for the case of Saturn. And that led to the formation of these features. For the case of Jupiter, the great red spot has been spotted for a long, long time, for about 300 years now, and it's still ongoing. A few years back, it shrunk in size, and people were, oh, maybe this thing is going to tame after all. So again, these are like the vortices that fall from the circulation of the air, but then it started to grow again. So you take several Earths and you place them in this thing. So these are huge hurricanes with extreme high speeds that are ridiculously high speeds. And the same thing is actually, at least in the poles of Saturn also exists there too, so it has similar features. So as a matter of fact, the winds are actually faster in here than that of the case of Jupiter. Again, inside you have all of these features in here, including the storms that form on the surface itself. And as I was saying, this whole mechanics, especially those metallic liquid hydrogen inside the cores, generate a ridiculous amount of magnetic field. And we saw in the picture from the beginning, from the James Webb, basically showing the auroras that form on the surface of, that forms in the poles of Jupiter. And also for the case of Saturn, also it has auroras, also at least those features on the surface. And for the case, at least for Jupiter, we know where it's coming from. It's coming from the moon Io, and actually have also Enceladus in here too, that is causing all kinds of stuff that is happening in there. Okay, so this is the unit from this week that I wanted to talk about, really the big giants, especially Jupiter and Saturn, excuse me, and what we learn from them, and the stuff that they tell us about it. Anything that we can discuss up to this point for the inner planets is different in terms of composition, in terms of density, in terms of the scale of things. Far bigger in terms of mass, far bigger in terms of volume, far bigger in terms of auroras, far bigger in terms of all of this winds, in terms of all of these features that they have. And the other two gas, basically, which are icy, more ice giants than gas giants, they're similar. They have fast winds. They also have, at least for the case of which one, Neptune, it has also something similar to the great red spot. I think they call it the great blue spot because it's a blue in color. They have it has similar, but it doesn't really last that long compared to Jupiter. It did not last that long, so they were pictured in the early missions, but then they disappeared. They appear in other places. The shapes of the other two are a little bit different colors because of the methane that is on their surface. So they're actually blue. Just when you have the flames in your home, if you guys have gas inside your home that you're using for your kitchen, you notice the flames that are coming are blue in color. That's because of the methane. That's exactly what these planets also have, this hue of that color too. So if you have enough oxygen, you could burn those planets, but of course it doesn't make sense because you don't have enough oxygen and even the temperature is not that high to really get them to burn chemically. Okay, so it's really ridiculous. But the point in here is that these are the two units. Next time when we meet on Thursday, we're going to talk about the moons, and you will see that the moons, if anything, are far more interesting, actually, honestly, than the planets are. And the moons, we're going to have all the outer moons. That's really the focus is, and they see that their main characteristics and how the rings form. There is a concept that we're going to explore next time, which is called the Roche Limit. And the Roche Limit tells us exactly how close a moon can be before it's dismantled into pieces, basically, and broken into tiny pieces to form the rings. So that explains the formation of the rings around these planets. And the rings at some point they would be there. In the beginning, they're a lot, and then they start to shrink with time. So basically either fall on the planet or basically they're falling on other objects. That's exactly what's happened to the other planets, or the other planets other than Saturn. Saturn is actually, its rings are more recent in a sense compared to the others, okay? So this is the unit for today. Any questions? If not, I'm gonna see you guys on Thursday at the same time. Okay, then you have a good rest of the day, and I'll see you guys next time this week. Okay, thank you.